in a different format than the usual one, just because it's Thanksgiving. And so everyone is invited. We'll have lunch together at the same time. And for today's speakers, Michael.
Yeah. Many of you probably recognize Daniel Jafferis. He's a string theorist here, a professor of physics at Harvard, and they will tell us about traversable wormholes.
All right, wonderful. Well, thank you so much for inviting me to speak at this new forum here, and it's great to see the big crowds of people. It's really a pleasure. So I'm going to tell you about some work I did with my student in Gao and with Aaron Wall, who's a postdoc at the Institute for Quasi. And the topic will be about traversable wormholes. This was a fun thing to work on because usually things like that, which sound cool, we usually say just totally impossible. And today I'm going to tell you that it is actually possible. Although I should make a disclaimer at the beginning, I'm not suggesting that we're going to make one anytime soon, even less suggesting that we see them in the sky. They're very fine-tuned, low entropy configurations, so you would have to make them. But it's not totally impossible. That's what I'm going to try to explain. Okay, so I think this is really the first example of, so traversable wormhole is maybe a slightly vague terminology, but I would say this is the first example where we can see that it can work. So it's embedded in some consistent quantum gravity system, gravity with some other fields in a way that it doesn't violate anything. And in order to make it work, it's crucial. So you should picture a wormhole. There's something like the Einstein-Rosen bridge that connects two black holes, two black hole interiors. And of course, in this maximally extended Schwarzschild spacetime, the Einstein-Rosen bridge is not traversable. You can't get through it. It's a spatial connection, but if you jump in, you just die inside. But what we'll do here is I'll try to show that if you have direct interaction between the two throats, the two near horizon regions, and by direct interaction I mean through the ambient spacetime, not to the wormhole, then there can be some negative energy that will violate the average null energy condition. And it's similar to the Casimir effect. The kind of negative energies you can get if I take two plates in a vacuum. I'll explain hopefully how that works. And then if I have time at the end, I'll describe some relations to quantum information theory. So what is the quantum information interpretation of what happens when you throw a qubit through a traversable wormhole? How should you understand that? And it's related to this relation called ER equals EPR. ER here is Einstein-Rosen, so it's like a wormhole, non-traversable wormhole, being the same thing as entanglement, like EPR entanglement, which was a proposal of Vaidya and Wang. But basically a relationship between quantum fields and geometry. So I'll mention some connections to that idea, and so if we get time, so maybe I will talk about it before I get to it. Okay, so I don't have any pretty pictures, I'm sorry to say, but I have some very poor pictures, which I drew. And so this is what I mean by wormhole. So something where the spatial cross-section looks like that. So there are two regions which are large, and then there's the throat which connects them, like this. And the two regions could be two different, otherwise totally disconnected asymptotic regions, or they could just be two places that are very distant or somewhat distant in the same component of space-time. So it could be I have one space and then two connecting two points. So I think we all know what this is supposed to look like. And the example I'm going to talk about, just for simplicity, I will assume that I'll look at a case where these two ends of the wormhole sit in an anti-de Sitter spacetime. That's not because what I'm saying is so specific to anti-de Sitter space, it just made the calculation easier. And it's also a situation where we understand quantum gravity rather well, and so we can be perhaps more sure that if we embed a configuration there, it really does make sense.
Is it relatively or it's stable?
Well,
it lives long enough.
Well, right. So I would say it's not stable, but the question is, does it live long enough for anything to get through it? So the kind of Penrose diagram I'll have in mind is one like this. So if this was a square, it would be the eternal Schwarzschild Penrose diagram, and then the wormhole is not traversable. But here, the question is it possible to get the diagram to look like this, elongated in time, so that it's traversable for a little while? But I wouldn't call it stable because after some point there is a horizon. If you wait too long, then you die instead of getting hurt. So it's not stable in that sense. It's not a time-independent metric, but still it could have traversability. The thing which is, so time-independent metric, that is probably possible. So this is the best you can do, but it's still kind of interesting. That's right. So that's why it's a especially fine-tuned configuration. So it will be very hard to make. In other words, this is, there's no problem with having this state in principle, but it's some particular state of this quantum system. It's a very fine-tuned state.
So just for pedagogical reasons, I think in the Rosen Einstein-Rosen bridge, that is off for a very short time.
Right. I mean, the Einstein-Rosen bridge is just there's no time when you can get through. So in that Penrose diagram, this horizon connects to this one. So no path could get from the left to the right. Any path from the left will end, back to the left, will end in the same way. So by traversable, I mean that if you solve causal path that can go from the left to the right. But this window may be very short. But notice that if you actually have this eternal space-time with the white hole in the path, then even if this time window is short, it corresponds to an infinite time on the left boundary. Basically because there's some huge redshift near the horizon, so as long as I jump in before some moment, I can get through. But obviously the lower down in time you go in this Penrose diagram, the more fine-tuned you have to imagine the configuration was. Right? This is the configuration you get like time evolving back, this black hole background. So it would be very hard to make a thing with this lower piece in the Penrose diagram.
But the proper time between the end of the past horizon and the beginning of the future horizon is fine.
This is fine. And short, it's a very short time unless you manage to achieve, I don't know how to prove any strict upper bound on this time, but in reasonable or in simple setups, it's a very short time. Okay, so that's the picture that we're aiming for. And let me just remind you a little bit why we usually think that it's hard to have traversable wormholes, why they don't work. And the basic reason is simple. It's because the ingoing, imagine I have light sheets that go into the wormhole on one side, they have to be focusing in, and if you're ever able to get out on the other side, you will eventually reach infinity on the other side, and the light rays have to then come out. So there has to be, at some point, along traversing the causal path, a defocusing of the light rays, and then by the Ricciardi equation, it means that there has to be negative null energy in the configuration. So for instance, along a null line that goes from one side to the other, the total integral of the null energy along that null line has to be negative. Okay, so that's the basic reason why these configurations look hard. Now, we know that in classical physics and classical theories, it seems very unreasonable to allow matter with negative null energy. To even contemplate that possibility, because it would seem to indicate an instability. So if I had classical fields where the local energy, null energy could be negative, or any energy could be negative, I could produce them and positive energy things together, and it sounds like it would be unstable. An instability to vacuum or some other technology. But in quantum physics and quantum field theory, there are always states in which, at least at one point in space-time, the null energy can be negative. So having negative null energy in quantum field theory is not exotic. It's easy to make those kind of states. A typical example are something like squeeze states. So if I have just some oscillator mode of a quantum field or something like that, if I wrote an expression like this, which was linear in the field creation and annihilation operators, that would make a coherent state, which is like the quantum state version of the classical configuration. Those would always have positive energies. But if I look at states like this, these squeeze states, it's basically like I change the width of the wave function, then it will often be the case that you can get negative energies. And in states like this, the energy oscillates between positive and negative, so the average energy is still positive. But at a point in time, at a given moment, the energy can be negative. Negative here means lower than the stress tensor in the vacuum configuration. And people make these squeeze states all the time. I mean, like people who do physics make these kind of states. But in order to have the traversable wormhole, the average null energy had to be negative, right? So you needed to have a total defocusing of the light rays. So it's not good enough to just have the null energy negative at a moment. It has to be negative all along the traversing null geodesic. And that sounds much harder. And in fact, basically people have proven that if the null geodesic is achronal, then it will always obey that the average null energy is positive. So achronal means that no two points on the geodesic are time-like related. So if we imagine a null line in flat space, of course, there's no straight null line in flat space. There's no time-like path between any 2 points. But I could imagine a null line that went in a kind of corkscrew or something like this. Then, of course, there can be time-like paths connecting points, even though the line is null. So if there do not have this time-like connection, it's achronal, and that's when the average null energy condition is obeyed. But note that in a wormhole configuration that connects where the 2 endpoints are in the same piece of space-time, it will never be in this achronal situation, because precisely because the wormhole looks like a loop on space. So if I go through a wormhole like that, there'll always be some time-like path that could have also connected pieces, or there could easily be such. Now, for simplicity...
Wait, did you say never? I thought you said never. It could never be achronal?
No, I guess it could be...
There are some that are geodesics that are not achronal, but...
It seems hard that it could, well, okay, maybe you could write down a metric where there would be achronal ones, and that will not be allowed by this result. Maybe I should say that. You know, a typical example where it would be achronal would be a picture like this, where if these are just 2 different asymptotic regions that don't talk to each other, then this geodesic will be achronal. In order to make it work, I will have to introduce a direct coupling between these 2 boundaries, which you can think of as a proxy in this picture, which I just used for calculational simplicity, for just the direct connection between the 2 throats of an ambient space-time. So you can think of this ADS region as the near horizon region of one black hole, this one is the near horizon region of the other black hole, and the direct coupling I put between them is like the coupling I would get by going through the ordinary space, not through the wormhole. So you could have that picture in mind if you don't like the idea of just sewing together ADS boundaries. But it's mathematically consistent to sew together ADS boundaries. Okay, so that's one kind of argument. So we'll evade it because in our situation the geodesic isn't achronal. And all I wanted to say is that what you might typically think of as a wormhole might often have the geodesics being not achronal. So maybe I shouldn't have taken this as such strong evidence that traversable wormholes are possible. Anyway, it rules out certain configurations, which will not be mine. And then another general rule that says that there's something hard about making traversable wormholes is the generalized second law. So the generalized second law is the statement that area plus entropy, plus the ordinary entropy, area plus entanglement entropy across some horizon is an increasing function. And so if we apply that in this kind of situation, it looks like, again, we'll have some contradiction because let's say we look at the horizon here. So the horizon is really this dashed red line, and we should continue it back. That's the actual horizon. So in the generalized second law says that the area plus entanglement entropy across that horizon should be increasing as you go up this horizon. And that's fine up here because the area goes to infinity, or the area could go to infinity up here when you approach the boundary. But it's a contradiction back here because the area is infinite in the past, so it can't be increasing. It's finite in the middle. And I'll explain to you later why. So what we're going to do is introduce some direct interaction that couples, say, this region to this region. By direct interaction, I mean we change the boundary conditions in the setup so that if a particle hits the left boundary, it doesn't always just bounce off. That's with standard ADS boundary conditions. There's some small amplitude that it could appear on the right. It's causal. It might not look local in the way I do this picture, but you can think of having sewn these two edges together. But that's actually a very natural way, if you like, of modeling what would happen in the conceptually similar but calculationally harder setup where I had two black holes in the same spacetime. Because in that case, I can send stuff from the vicinity of one to the vicinity of the other, not just through the wormhole, but through the ambient space. So the connection between here and here is like the connection in the ambient space. Right, so if I, suppose I look at a sphere of some fixed distance from the horizon, so it, will go along some hyperboloid like this, some hyperboloid like that. The important point is just that there's another way of sending the signal than through the wormhole. You can also go around. But that would be typical, that would always work like that if the two black holes are in the same component space. So here I separated them and introduced it sort of artificially just to get a more controlled setup where we can do the calculation. Well, also, as a string theorist, we like ADS, but for other reasons. And another thing that could be bad about traversable wormholes is that just can't see the clock. Another thing that could be bad about traversable wormholes is that there is some risk that you could construct time machines by applying a relative boost. So if I thought that I supported it by some exotic matter that only lived in the throw, you might think I could boost one end and not the other and still get a valid configuration. That would be bad because I could boost one end so that the signals came out from the past of the other side. That won't happen here because the negative energy that supports the configuration sort of depends crucially on the global structure of the space. And if I do this relative boost, it won't work. It will not be an invariance of the configuration. Okay, so as I said, for simplicity, I will start with the eternal ADS black hole. That's the thing which has the Penrose diagram like what I drew, but where it's a square and not an elongated rectangle. And in a sense, the eternal ADS black hole is on the edge of traversability. That's because it has killing symmetry, the symmetry that goes up in time on the right and down in time on the left, space-like behind the horizon. And there's a bifurcation surface, point where the two horizons cross. And the fact that the two horizons cross says that it's on the edge of being traversable, right? If you slightly elongate it in the diagram, it will become traversable. If you make it wider, then it will be some longer throat, which you're even less able to get through. Okay, I'll skip the last remark. In this particular background, you can see very, very explicitly why the average null energy along the original horizon is the thing that controls whether the configuration is traversable or not. The idea is that, imagine we get some small perturbation of the metric. Well, we turn on some matter stress tensor in this background, and then it will backreact on the metric. We'll get a small change in the metric. The thing that determines traversability is, again, just this question of whether it elongates the diagram up or it makes it wider. So if it goes up, it makes it traversable. And mathematically, if you compute the integral along the original horizon of the perturbation of the metric, HUU, if that's positive or negative, that determines whether the elongation is up or wider. And then the linearized Einstein equation just directly relates that to some constant times the average null energy. So when the average null energy, when this right-hand side is negative, it says that this guy is negative, and that says that the light ray tips down and reaches the other boundary. So that's the story of it. So that's, I think, physics. I'm just restating the Ricciarduri equation that if I have negative null energy along the line, it makes the light ray bend outward. But of course, we don't expect that by making some change of the. So what I'm going to do is I'm going to start with this background, and then I will imagine I have some other matter fields that live there, some quantum fields, and I will try to see, well, can I construct a stress tensor out of these quantum fields that will have the average null energy negative. But of course, from the arguments, the things I just said, there isn't any state of the quantum fields without adding this extra coupling between the boundaries. There's no state of the decoupled system, one where the two boundaries are not directly connected, in which the wormhole will be traversable. Well, there are a lot of ways of seeing that. One of them is because the average null energy condition, the positivity of the average null energy in that situation is like a theorem, or alternatively, it will contradict the fact that I said there's no interaction between the boundary quantum systems. So if I can send signals to the interior, it means that the two boundary quantum systems do interact. From the point of view of ADS-CFT, that would not make any sense. But even in a sense, the gravitational way of understanding it is that in gravity, the Hamiltonian is a total derivative, so it equals a boundary term. And so if I have a spacetime with two boundaries, the total Hamiltonian is just the sum of a left and a right boundary Hamiltonian. And so therefore, it should be impossible to ever send a signal from the left to the right, because there's no coupling term between the left and the right Hamiltonians. That's just because the gravitational Hamiltonian, the bulk, is a total derivative, or it equals a boundary. So it better not be that I can find a quantum state of some field in this background which has a negative average null energy. And indeed you cannot. It's easy to see that the average null energy operator, if you like, has the what I call the thermophile double state, or what you might just call the black hole vacuum in this eternal ADS black hole. It has that as an eigenstate with zero eigenvalue. So it is the minimum. So then in the Euclidean vacuum and the eternal ADS black hole, the average null energy is zero, and that is the minimum value for any state. So any other state, it will be positive. And now, at linear order, if I imagine I change the state, there's a reason why I go through this. If you imagine I change the state a little bit, say by acting as unitary. Why is this there? Right, but it just happens to annihilate the Euclidean vacuum. It's basically because of the Killing symmetry. It's because the existence of the Killing symmetry tells you there has to be a bifurcation surface, and so the average null energy should be zero exactly. Well, I mean, you can also just prove this.
This is on the horizon.
This is on the horizon. On the horizon. You can prove this pretty easily. Of course, I don't have time to explain it right now. So if I looked at a small change in the state, imagine I act on it with unitary operator like e to the I small parameter times a, where a is anything, then the change in the average null energy would be given by the usual commutator formula. So at linear order, it's zero, because this is the minimum value of the energy. Okay, but now imagine instead I turn on this coupling between the boundaries. So we imagine in the past, we start with the decoupled system, and we start in the Euclidean vacuum of that black hole. And then after some moment, we turn on this coupling that interacts the boundaries. And the meaning of this coupling is just that, again, there's some amplitude of transmission of a different particle, some scalar, let's say, that hits the right boundary. There's some amplitude h that it will appear out of the right boundary. So I meant from left to right, or from right to left. I think I said from right to right. If you wrote it at the level of fields in this background, you would say that you modify the boundary conditions in this way, but I don't know what in other time. But what actually is my timing? Did we start at exactly 1:30?
Yeah, maybe 5 minutes.
Okay, so in a situation like this, of course, that linear order and turning on a perturbation to the Hamiltonian, it again changes the expectation value of operators by the commutator, but it's only the commutator in the future. So turning on this interaction doesn't change the state of the past, of course, just changes it later. And so now you won't get with the cancellation that made the change in the average null energy have to be 0 on the previous transparency. So now it doesn't have to be 0. You'll get something non-zero linear order in general, and turning on this kind of coupling. And then you can just adjust the sign to make it negative. So it shouldn't be hard to make it negative. Of course, the amount might be tiny, right? So this is some quantum stress tensor. And then we'll look at its gravitational backreaction. So it's a gravitational effect from a quantum stress tensor.
But I guess this is your whole point, that it's weird that doing something out at infinity, coupling the two boundaries, would change what you could do at the horizon.
Yeah, well, the causality of it makes perfect sense, but maybe I'll get to that on a couple more slides, and I think I'll explain why. Of course, when you do something on the boundary, it doesn't change anything immediately. It only changes something later along the horizon. Just to say that now. So all the effects look perfectly causal in the ball. It's just that, the horizon, the location of the horizon is TV logical. Right? Okay, so I won't belabor this. We actually worked out all of the details in an example in three-dimensional gravity, but that was just to make the formulas easier. And the end result is that, this is the most important picture, just that we had various parameters. We considered turning on the deformation at different times, turning it on and turning it off, and the average null energy, is something non-zero. And since this is a linear order calculation, of course, you get to pick the sign. So we picked it negative. And then if you go to higher orders, there may be some quadratic contributions, so it's not clear how negative it could be. But there don't seem to be any general theorems that bound it as far as we could tell. But it might be very hard in some sense to make it very negative. Okay, so this is the picture where I think I'll answer Andy's question. So here I do not the Penrose diagram, but the diagram in just some coordinate system, which is actually the Penrose diagram of the original black hole before I turned on the perturbation. So this looks like the Penrose diagram of just the eternal ADS Schwarzschild, but now when I turn on this interaction during the red interval, it makes some squeeze state of the quantum fields in this background, which propagates causally up this way and this way. And when that backreaction of that undermetric causes the rays to bend out, and so the horizon, the original horizon was this purple line, now that ray can traverse the wormhole and come up here, and then the final horizon is this orange line, which comes from this locus. Okay, so everything is totally causal in the bulk. In the sort of pale yellow shaded region, by causality, nothing is different. It looks like the eternal black hole in the original state. But this squeeze state propagating here causes these light rays to bend out. So it's just the same as if I said I threw in some classical negative energy pulse, but that's not allowed by self-consistency, but this thing is allowed. Okay, of course, if I just took, the top chunk of the diagram, I won't know whether it's traversable or not. Right? That's a global question. I have to put the whole picture together. Because obviously, after I show the interaction, I could just interpret the system as a state into decoupled, without the interaction in the decoupled system again, and then I would think it's not traversable. But if I just only look at that causal picture, I just can't tell. Right? So traversability is a property of the total spacetime. Now, this window here, which you might measure the null length of this window, something like that, is small, right? Of course, it's the gravitational backreaction to the squeeze state. And also, the squeeze state was not really focused in the black hole. It's spread out through this entire ADS space-time, and so there's also some suppression factor related to the radius of the ADS, and some d, which is the dimension of the space-time. Okay, so this window is short if this h is something small. Like if this h is order 1, then this is something very small. But you might try to make it larger. I mean, this is just a simple setup with spherical symmetry where most of the cancellary energy is spread throughout the space-time. So maybe that could be better. But okay, so from the point of view of some test particle, if you have just a test particle that you don't look at its own back reaction, it can get thrown. So you just jump in early enough, and there's some window.
Could you explain the dimensions of that formula? That's the time shift?
Yeah, that was supposed to be this time window. And if it's not dimensionally correct, it's probably a factor of Planck.
Or LADS?
No, I mean R is like LADS.
I'd be surprised if it wasn't linear geometry.
Yeah.
So if we work in Planck units, the size of this is 1 over the ADS line, which you might expect.
I think that's correct.
But does that mean it's parametrically small compared to the Planck line?
Okay, I have to think about that question.
It better be bigger than the Planck point, otherwise you have to be a black hole to get through, right?
Well, I should say, of course, you're hugely.
No, electrons have Compton wavelength.
If you get, so if you jump in very early, you will be hugely length contracted, if you like. So it's easier for you to fit through a small aperture. So in this picture, maybe you could throw an elephant in, because the elephant fit in early enough. By the time it gets near this bifurcation surface, it's hugely length contracted, it can fit through an arbitrarily small aperture. But I mean, what it means is that you have to jump in sort of before a scrambling time or something. But the horizon size can be large. So the horizon size is a transverse direction, that's arbitrarily large. So it's really just a short duration. That's why it's not so hard to get through if you're a test particle. What the thing you should really worry about, the more invariant question than this question of the size, is what does the collision look like between something trying to get through and this negative energy squeeze state on this side? And so that will have
Oh, wait, there isn't a coordinate invariant notion of that size, right? You could take the proper time length distance.
Right, but it's a time window, it's not a slide. So the transverse,
It's a time window,
the
right.
size of the elephant is controlled by whether it is directions, which are arbitrarily, those are macroscopic. The directions this way, which is the horizon radius, is some macroscopic size.
Right, but the time window,
The time window
the
is
proper
short.
time window is
But-
coordinate invariant.
Right, so it just means you have to go through very close to the speed of light. But you can throw an arbitrarily big object through close to the speed of light. You don't have any invariant time window length, right?
I don't believe you can get to a window that is parametrically short relative to the Planck's time.
I don't think it's parametrically short. I think it's maybe.
Well, that's the formula.
You can just get really boosted.
Well, anyway, I think this energy question is the more important question, because the other thing is.
Anyway, it's a point model. It's a point of principle, it seems.
So,
It can be.
yeah, of course. I'm not
Yeah.
suggesting that you construct it, but
No,
even
no.
as a point of principle, it turns
It's a
out
point of principle.
that the time is smaller than the Planck time or something. Doesn't mean anything. So anyway, so there is some interaction, of course, between. So we can try to analyze this in a different way. We send some test particle in, and then it interacts with the squeeze state. We ask what happens. And the question is there a regime of energies? The energy is really controlled by how early we jump in. Is there a regime of energies in which the interaction is dominated by the Einstein approximation? In other words, the main effect is the gravitational deflection that I drew in the picture, rather than something like collapse into a black hole because of the collision. And the answer to that seems to be yes. So there's some finite window where the dominant effect is the gravitational deflection. If you jump in even earlier, more scrambling times in the past, then instead of then the higher order contributions will be important, and maybe you'll just collapse into a black hole when you hit this squeeze state of these quantum fields. But it looks like there is a window where you can get through, and the time you have to jump in is something like a scrambling time. Yeah.
I mean, the whole key here is that this squeezed quantum state has got negative energy,
Yeah.
and you're using Raychaudhuri's equation to say
Right,
for
exactly.
defocus. Is there any doubt on that issue? I mean, is
No,
this
that's
negative energy
clear.
really like a classical negative energy or not?
Well, so
Because only the, I think Raychaudhuri was doing the
Right.
classical problem.
Right, of course. I mean, I can say two things in answer to that. One of them is, of course, when you have a quantum state which say has negative energy, what I really mean, the expectation value of the energy is negative. And so that might mean that sometimes when you measure it, the energy could be negative, sometimes positive, but the average is negative. But at least if the average is negative, it must sometimes be negative. Okay, so that's the trivial remark. But more meaningfully, it's about the question of whether drawing this Penrose diagram, which is really showing you the gravitational reflection, is the main effect, or if some higher order quantum gravity effect is important in this interaction.
Yeah, I'm asking about
So-
the main effect itself.
Right.
Why should Raychaudhuri apply to this funny quantum state?
Oh, I see. No, I think I mean in perturbative quantum gravity, we just promoted the Einstein equation effectively to an operator equation, and you will find that the expectation value of the deflection is going to be related to the expectation value of the null energy.
And if it's negative,
Especially in this linearized regime, that's completely clear.
How sensitive it is with respect to the particular interaction you pose?
The interaction, the boundary interaction, that probably may not matter very much. We chose the simplest thing, which is really hardly deserves the name of an interaction. It just says that there is an amplitude that you can go from here to here. In other words, it's like we just sold the two red intervals together with the transmission amplitude. It's a linear interaction. So the scalar field we imagine in living here supports the matter stress tensor just obeys the linear equation function. So it's not a nonlinear. You could also contemplate something more complicated. So probably in the interest of time, I should just stop here. I guess I don't need to tell you about the quantum information interpretation because we ran out. This seems like a good place to stop as far as the discussion of the wormhole geometry goes. So I hope I convinced you that with setups like this, it is possible in principle to have traversability. And I think it would be extremely interesting to, say, try to bound how much quantum information could actually get through. So can I send, how many qubits could I send through this wormhole? Okay, so thanks for listening.
Time for one or two more questions.
Good question. So, if you had a lot of these, I suppose that there'd be some observational component to it on the sky. Maybe a cosmic microwave background from this part would be correlated with that part.
Right.
And you can say, well, there can't be a zillion of these, right? Because otherwise it would change the temperature of the cosmic microwave background radiation.
I agree with that in principle. I just think this is a very fine-tuned configuration, as you can see, because of the. I mean, you don't actually need the white ball, but you need some past piece of this Penrose diagram. So it's a very low entropy state that seems extremely unlikely to me to have arisen naturally. But of course, we can produce very low entropy states, but I think higher entropy somewhere else. But I think it would be hard to imagine them being produced by nature.
What would maybe lack?
But maybe. Of course, if you had one of these and this time window was long enough, then you will see some effect. Yeah.
I just wanted to understand this achronal condition. that you had. So, thought experiment. If I'm sitting in a Schwarzschild spacetime at the photon orbit,
Okay.
I can have photons that go around and come back to the same space point at a later time. And I could have an observer with a rocket sitting there, using having an actual time-like interval to this new location of the photon. So is that
would
an
be
example of something that is not achronal?
exactly.
So black hole spacetimes are not achronal.
No. So sorry. So the chronality or not isn't a property of the space-time. It's a property of the geodesic. So in any space-time, there will usually be both some chronal and some achronal lines.
I see.
It's just the question of whether, so in a particular path, if that path is achronal, then we think the average null energy has to be positive. But of course, there will always be some paths through it.
Okay, but would you then say that you cannot have traversable paths that go from one photon orbit to another?
No. So the guys where you can't have it. So if you had a traversable wormhole where all of the paths through it were achronal, that would be impossible. But if the traversing paths are chronal, then it could work.
Oh, I see.
So
Okay,
it's,
I got it.
it's
Okay, fine. Fine.
So, oh yeah, I think in the interest of time, we'll have to move on, but let's thank Daniel again. So in the rich tradition of our visiting math speakers, the next speaker will be doing a Blackboard talk, so maybe start to rearrange the room.
Whiteboard or blackboard?
Actually, Blackboard this
Blackboard.
time.
Mu-Tao Wang is visiting us from Columbia University. Professor Wang did his PhD here at Harvard with Professor Yao. He then went on to do a postdoc at Stanford before joining as faculty in the math department at Columbia. He has had a rich career where he's been felicitated many times. He's now a member of the American Mathematical Society. He's also winner of the Chen Prize and the Morningside Gold Medal for Mathematics. And he's done very important work in differential geometry, and in particular in GR, in general relativity. He's done fascinating work with Professor Yao on quasi-local mass, and today he's going to give us some insights on that. So we're very pleased to have you.
Okay, well, it's very nice to visit the BHI for the first time. I have to start by thanking the introduction, and thanks for the invitation. So I like to talk about this notion of quasi-local mass, and now infinity. Fair enough.
Try the first one.
Sorry for a change of direction on the election day. Okay, so let's see. So suppose we're looking at an isolated system, and there's some astronomical event. That is happening here, and light rays emitted from this astronomical event. And we observers, we're situated at now infinity. Okay, suppose this is us. And well, so a traditional description of now infinity is the following, or in terms of boundary size coordinates. So we take this UR, and then we make x2 as 3, x2 will be theta, x3 will be phi. And then our space-time metric near now infinity is of this form. With suitable asymptotics. So, for example, U is you can do everything in terms of R still go to infinity. So you do expansion in terms of inverse power of R. So U is going to be 1 minus 2 and theta phi divided by R for some lower order term. And V will start with 1. Let me just elate the lower order term. As sigma AB, dxa, dxb, just a standard row metric. Okay, and also this WA will start with 0. So this is a description of yes.
Of capital U should be du square, right?
Yeah, sorry. Thank you. Okay. So this is a classical description of non-infinity, and under this assumption, you can define the boundary mass at a cut. Okay, so this is going to be my u equal u naught. So I'm gonna, once we have a cut here, I can integrate this function. This is a so-called mass aspect function. Straight over 4 pi m u theta phi. Integrate along this sphere at infinity. Okay. So in particular here I have m0 theta phi. And also I have the mass loss formula. Okay, so du of mu is less than or equal to 0. So when you move in the du direction, this mass is actually decreasing. So this is actually the first, well, I'm a mathematician, so this is the first convincing argument of the existence of gravitational wave, I think, to most mathematicians. But let's look at this whole picture here. We talk about this bonding sex coordinate system. You define this bonding mass and this mass loss formula. All of these systems actually require some global knowledge of future null infinity. In a way, you need to know all directions. You need to obtain a statement like this. And our idea is that we are going to consider quasi-local mass in a single direction. Okay? Hoping that we can actually get some point-wise statement or point-wise quantity and null infinity. So we consider quasi-local mass along a single direction. Hoping that we can get some kind of point-wise quantity ascribed. So that's the upshot. Okay. So and we actually obtain two calculations. One is for linear gravitational perturbation of Schwarzschild or Kerr, and the other is for Vaidya spacetime. Okay. And turn out the statement were actually quite interesting. So I'll talk about these results later. But before, just let me just roughly describe what this quasi-local mass is. So what is the quantity we're trying to evaluate? Okay. So this is actually this quasi-local mass is actually with respect to a surface. So yeah, I think I can erase this part here. I want to keep this picture. So the idea is that, well, because there's no gravitational density, so you're just hoping for the second best. You want to be able to describe energy or describe mass quasi-locally. So what you do is you enclose a space-time region by a sphere, hoping that you will be able to read off gravitational energy, gravitational mass from the boundary two surface. So we actually consider the sigma here is a two surface in space-time. It's just going to be like a round sphere that you're familiar with. But the thing is that this surface here is going to have a different intrinsic geometry and different extrinsic geometry. Okay? And we're hoping that we'll be able to read off gravitational energy from this information. So with different intrinsic and extrinsic geometry. And in the evaluation, the only intrinsic geometry we need is actually the induced metric. So this is the induced Riemannian metric. So we're a two-dimensional sphere sitting in Lorentz space-time, and we assume it's space-like. So acquire a Riemannian metric on this two-dimensional surface. It's not going to be the standard round surface. It's going to be distorted a little bit, but that's fine. So just take this information, and we are also going to take another geometric quantity that would actually tell us about the extrinsic geometry. So this is what we call a mean curvature vector. So it really comes from differential geometry, but this is really just a normal vector field. And that can be, we actually take into account of all null expansions. So you look at null expansions in all null direction, take them together, and that will actually give you a normal vector field, and that is the mean curvature vector field. And of course, we know this is, this tells us about the extrinsic geometry in the space-time. This null expansion will tell you how this gravitational field distort your surface when you move the surface in the null direction. Okay. And so let me just tell you this mathematical theory that we have. So we start with some physical data. This consists of the surface here, and the induced metric, and the mean curvature vector that actually has all the information of null expansion. Okay, I'm going to draw a big black box here. Okay, and these are all the mathematical theory that we have been developing. So basically, once you have this data, this geometric data here, we actually solve a differential equation. So this is actually a PDE system. We call it optimal isometric embedding. Okay, this is actually a quite complicated partial differential equation that consists of 4 unknowns and 4 equations, and actually all the equations are unknown, and some of them are of higher order. But I think after years of study, we have a pretty good understanding of this system. And in particular, if you work with any weak field limit perturbative configuration, we can actually solve these systems in a very nice way, and sometimes very explicit. And that's actually what I'm going to talk about. But what does this solution of this PDE system tell you? It will actually give you another surface in a Minkowski spacetime. I use R21 for Minkowski. So this is the definition in any energy. You have to have a reference system. So we're using the Minkowski, the flat spacetime, as our reference. And in this way, once we have this data here, we actually get another surface that is in the Minkowski spacetime. And it actually has exactly the same induced metric. Okay, and after this black box, we are going to compute the mean curvature of this new surface here. So this is a surface that's in a totally different spacetime, in the reference spacetime. Okay. And at the end, we just use this sigma and h and h0 to evaluate the quasi-local mass. And this expression actually goes back to the Hamilton-Jacobi analysis of the gravitational functional. But I'm not going to say too much about it, but it turns out this quasi-local mass is actually expressed as a difference of 2 quantities. One, we involve the information of this physical surface, and the other, we involve the information of this reference surface here. And 2 remarks are in order. Well, first of all, we consider this as finding a reference for defining energy. So we start with this physical surface here, and this one here is considered to be the best match of your physical surface. Okay, and this is actually a canonical procedure to find its best match. And in fact, if your surface here happen to be a surface in the Minkowski space, this procedure will find a unique surface that is itself. So you'll be able to recover yourself after this procedure. And so we have a physical surface here, and we have a reference surface here, and we just use the difference of the extrinsic and the difference of extrinsic geometry to determine the gravitational energy. And second remark, well, as I just mentioned, this quasi-local mass is actually the difference of these two quantities. In fact, if you like, I mean, probably a more preliminary version would be the Brown-York mass, which is the difference of two integral mean curvature. But you know, one sort of vindication of this this definition is that we can actually prove positivity. So this quasi-local mass is always non-negative if this space-time you start with satisfies the dominant energy condition. Okay, and also if you're actually a surface is actually in the Minkowski space-time, then the mass is going to be equal to 0.
And then does this notion of mass coincide with for some standard configuration?
Right. You coincide with the Brown-York. Yeah. But in a way, it just gives you a more refined way. For Brown-York, you can see some, you know, some funny behavior for Brown-York. So, for example, if you just take a standard light cone in Minkowski space, and you just take a cross section, that is not wrong, and then you will see that the Brown-York mass is always strictly positive. Okay, and that's somehow, you know, it doesn't really anchor the ground state for surfaces in the Minkowski space. Okay, so this is a very brief introduction of this notion of quasi-local mass. And by the way, I
One more
mention this. This is actually this is our joint work with supporting Chen and Professor Yao.
One more question.
Sure.
If you embed, let's imagine a de Sitter space,
Yeah.
like we are having now in the universe.
Right. Right.
Where, so is it guaranteed that the value will always be positive because you have a negative energy density associated with vacuum?
Yeah.
So what happens then to your theorem?
Well, first of all, you have to pick a right reference space. Well, you can pick a Minkowski as a reference, or if you have a perturbation of de Sitter, then you can use the de Sitter as a reference space. Okay.
But you'll always get a positive mass?
Well, if we use, well, in that case, the case we look at is just look at a perturbation of, for example, Schwarzschild de Sitter, and we use de Sitter as a reference space. And we can get some positivity when you're actually close to the, for example, to the cosmological horizon. But if you go beyond the expansion region, then we don't know. Okay, so this is a very brief introduction of the quasi-local mass. But let's back to this picture of isolated system. Okay, so what kind of quasi-local limit mass we're going to evaluate? So we can just starting from a physical space-time, I just take a null geodesic. So yeah, maybe I can erase this part again.
So just understand, these
Sure.
books also give you a reference H0. So H0.
Right. It will give you a surface, and then you compute the mean curvature vector of the surface. Okay. So let's back to this picture of isolated system. So let's consider a null geodesic. So let's say gamma of S. Okay. That approaches square plus. Okay. So it's just like for example, a null geodesic on one of a cup. Goes all the way to infinity, and then we take a two-sphere around each point gamma of S. So, for example, if this is a null geodesic, then for each point here, this is a gamma S. I just take a round sphere that is of unit size. And then I push all the way to now infinity and evaluate the limit of the quasi-local mass of this sphere. So let's call this one here sigma of S, and evaluate the quasi-local mass, the limit of the quasi-local mass of sigma of S. Okay, and we actually obtain two quantities. So this S here is going to be a phi parameter, so it's just comparable to the distance to the source. Well, the first one, of course, is just the quasi-local mass itself, and it's actually of the order of 1 over S squared. As I say, S will approximate to the distance to the source. And the important thing here is, of course, this M of S, sigma S, is going to be non-negative. And we actually have a second quantity. Okay. Because of this order here, the 1 over S term always vanishes. So we by exploiting the vanishing of the 1 over S term, we actually obtain the loop integral for any loop on the limiting surface. So what happens is that I take a unit size sphere here and I push all the way to infinity. As long as I'm actually in a isolated system, so there's a weak field limit. So the limiting configuration of this surface here is going to be just like a standard R3 in standard around R3 surface in R3. Okay, and for this limiting surface here, I can just take any loop. Okay, and I can evaluate a loop integral. Okay, so this is basically coming from this the vanishing term here, because you have an integral that is always vanishing on your two-dimensional sphere. So you can take a loop and cut it into two parts. Okay, and you're going to get a quantity that depending on only on this this loop here. And this quantity here is actually of the order of 1 over S. So it's actually of a higher order. Okay, so let me tell you this the result. I have, how much time do I have?
About 10 minutes.
About 10 minutes. Okay, thank you. Limited space. I don't want to write over there because people probably won't be able to see.
No, we can see it.
You can see it. Okay. So we evaluate two cases. Okay. So the first case is a linear gravitational perturbation. Of Schwarzschild curve. We actually follow Chandrasekhar's approach. Okay. So you take your, for example, you take your Schwarzschild here, and you look at the linearized vacuum Einstein equation. Okay. And in the case of Chandrasekhar, so you solve the linearized vacuum Einstein equation. And actually use a separation of variable. Okay, and you obtain a lot of linear waves. Okay, and it turned out in this case, we can actually work out everything for the optimized geometric embedding system. It really just reduced to solving two fourth order equation on the sphere, and in fact you can just do a spherical harmonic decomposition, and you'll be able to solve everything. and you can plug into the expression for the quasi-local mass. And so what the result that we have is the following. So first of all, this quasi-local mass just recover all the distinctive features of the waves. So in the case of Chandrasekhar, these waves, they contain parameters such as frequency and such as mode. But you can recover, you can read off all this information from the limit of quasi-local mass. And the second conclusion that we have, everything is actually quite interesting. So Chandrasekhar considered two kinds of perturbation. One you call axial perturbation, the other is polar perturbation. It turns out the linear Einstein equation actually decouples under these two perturbations. And the axial perturbation is fine, we get every result. But for the polar perturbation, we realized that this polar perturbation, they are actually not integrable using the positivity of quasi-local mass.
What exactly do you mean by not integrable?
Okay, you take your linearized Einstein equation, you solve for this linear equation, but not every solution comes from one parameter family of actual vacuum space-time. Okay. So not every linearized solution of a PDE is actually integrable. Okay. But this positive quasi-local mass applies to just assume the dominant energy condition. So if this one here can really be realized as expansion for an actual space-time perturbation, the quasi-local mass will have to be positive. But this is actually not true for the polar perturbation. Okay. So if you look at these two perturbations, they look almost like the same. I mean, but it turns out some of them are actually integrable and the others are not. And axials are, I mean, they're presumably integrable because there's no contradiction with the positivity of quasi-local mass. But we know for sure those polar perturbation, although you can solve everything explicitly, they just don't come from an actual family of gravitational perturbation of Schwarzschild. Okay? So that's the result for the linear perturbation of Schwarzschild. And we look at the other case, that is we look at a Vaidya spacetime. Okay? So you recall Vaidya spacetime. Spherical symmetric spacetime with radiation, and we compute the quasi-local mass of this one here, and well, naively, if you just make a guess of what is quasi-local mass here, I mean, look at this picture here. Okay, you just take in one particular direction. A very naive guess for the answer would be, well, you should recover the mass aspect function, because that's a function defined in now infinity pointwise. And you should get the mass aspect function. But turns out it's actually wrong. Because our quasi-local mass is always positive, while the mass aspect function is not positive pointwise. You do have the positivity of the bounding mass, but that is a global statement. You have to integrate the mass aspect function in order to get a positive number. But there's no guarantee that each one of them is actually a positive. So it's actually to our surprise that after we do the computation, we are going to get a positive quantity, and what that positive quantity is. And it turns out the answer is well, there's a constant here, but the answer is du mu times the positive function of S2. So the positivity of quasi-local mass indeed is actually related to bounding mass formula. Okay, and that is independent of the positivity of bounding mass.
What is this function? Depends on it.
This is a mu. This is a mass aspect function in the Vaidya space-time.
No, the other one. X squared.
This is just a constant here.
F.
Well, f is a function depending on the angle. I mean, we're not really localized to a point. So the different direction will have some effect. But this is just a positive function defined on your two-dimensional sphere. So this is actually the So this is turned out to be the mass. So the quasi-local mass is actually correspond to the because we have a negative sign here, and you recall by bounding law mass loss formula, this is always negative, and therefore this is actually a positive quantity. And it turns out the mass aspect function is recovered in this loop integral. Okay, so we can actually reproduce the mass aspect function, which is not necessarily a positive function, but there's no guarantee this loop integral is a positive function.
So this derivative that you have there in the integral is just, by the continuity equation, it's just the mass flux through the boundary, and you are just summing over the boundary. That's basically what you do.
No, this sphere is actually a unit-size sphere. I mean, I'm sorry. In the bounding mass formula, you're integrating along this one here, and that other S2 is this small S2.
The du mu u is the sort of can be thought of the time derivative of the mass. Right?
Yeah, that's right.
So by mass conservation, it should be the flux equal to
the
divergence of the flux. So this integral is the integral on the divergence of the mass flux.
Yeah, but what I'm saying that it's not it's not a mass aspect function just because of this positivity. We expect to get a positivity function, right? Okay, yeah. So our current project is just try to extend this project, to look at other space-time, because in this way we really get something about now infinity that is actually a quasi-local information. That doesn't correspond to the global. So we are actually looking at, for example, the Robinson-Traubman space-time, okay, and to see what kind of limit of quasi-local mass you're going to get over there. And the interesting thing here is that the whole metric is actually governed by a partial differential equation along the null hypersurface. So you'll be interested to understand how the initial condition and the value at the null infinity. And also for this linear gravitational perturbation, in the case of Chandrasekhar, it's really taking a partial Fourier transform with respect to the t variable, the time variable. So that's why this wave, they have this frequency parameter over there. But right now we can, with my two brighter students, they can really solve the dynamical equation. You can put back the t dependence there and just solve the hyperbolic equation directly. So hopefully we will be able to get more refined information at null infinity. So I think my time is up. I'll just stop there. Thank you.
Questions for Professor Wang?
I have a question. This expansion in S. So I want to understand whether the family of how many parameters can run. I mean, your solution is a parametric family of solution which has one vacuum.
No, I'm just doing vacuum perturbation.
Yeah, but you can have two parameters, for instance. Namely, for instance, you can when you say kerr there, you mean that you can vary
right.
mass and the angular momentum.
Right, that's right.
In the case of Brown-York stress tensor, you can also compute an unconserved charge, like for instance, angular momentum. In that case, it also matches.
Yeah, we look at the first order term, and the only information is the mass. And presumably, if you calculate next order term, you'll be able to recover other conserved quantity.
You mentioned that the du m being negative is evidence for gravitational waves, proof that but in principle it could be any radiation that is leaving the system, any form of energy. Why do you say gravitational waves? Why?
Well, I'm talking about vacuum case.
That'd be pure gravity.
I'm talking pure gravity. Yeah.
Okay.
Yeah.
Any more questions?
I mean, that's the one that is more acceptable to mathematicians.
Okay. But in reality, it could be any form of energy.
Yeah, right. But if you vacuum space-time, you can still produce this this loss formula. That's a good indication.
Right, so no more questions. Let's thank both our speakers.
This is so good. Not too mathematical.
I have a brief question.
Thanks again for talking on short notice.
Oh, no, yeah, that was great.
This is Bondi mass.
Yeah.
So the idea of the
Yeah, if
Bondi
you
mass
know,
can
you know,
depend
postdocs
on
or
theta
grad
and
students
phi.
also who are working on, you know, flexible,
Oh,
friendly
sure.
topics.
They say that it's not just
recommending,
it's mass at infinity, but it depends on which direction.
No, well, Bondi mass really is an integral.
Oh yeah, but there is aspect.
That is an aspect, yeah, the aspect, yeah.
yeah, well,
Because to me it seems if I have a compact mass which is
oh yeah.
asymptotically flat, there should not be any aspect dependence. Why is there an aspect dependence?
Well,
Physically, I'm not able to see why you should have.
I think I would say the gravitational wave actually come from the inhomogeneity
Waves, yeah.
of geometry, right?
But if I don't have waves, I'm really asymptotically flat, so just
Right.
time independent, whatever.
Yeah,
So no gravitational waves at infinity.
right.
Is there any aspect dependence?
No, in that case, you just have a single problem, especially if you're especially infinity.
Does that
Yes,
mean that
yeah.
when we
But then you
Right.
would be
Yeah,
independent.
yeah, I think especially infinity, right? But now infinity, I think the story will be different. Now infinity, when you have your radiation, that would be different. Yeah.
Because you can have radiation going out.
Right, and then
And it may not be isotropic.
yeah.
Something may go with it.
In that case, and you can have examples.
Yeah, because physically I'm not able to catch what the fuck is.
Yeah.
Yeah, okay. So it is the null infinity.
Right.
Not well, no. I met him once or twice, that's all. He's senior. Many decades above before me.
He's probably having a year years now then.
No, I know he must be. Born in 19.
He's around the
10.
same.
Yeah, maybe 106 or something. Yeah, 1910 and he was.
Still, that Chandrasekhar is actually his first name, not his last name. That way, I told him. Is that? Yeah.
S is probably some
Subramanian.
Is it Subramanian? Okay, yeah.
What is that?
I think that's just his name, Subramanian. So I think in their tradition, or our tradition, we put the father's name first and then your own first name.
Your own first name?
Yeah.
Okay, so that's actually his first name.
Yeah. So Subramanian would have been his father.
Very nice, yeah, thank you.
Thank you.
Null infinity and spatial infinity.
Yeah, it's very interesting and confusing.
It's crazy, yeah. Just one point.
Right.
Okay, good.
Yeah, I think so. Yeah, my computer didn't have admin rights to my computer, so Randall's helping me. So once he's done, then I'll check it. So.
Okay, yeah. And in 2 weeks you will arrive. Now next week I won't be here, but
Okay. Right. Yeah, and I made a note as to how you'd like it set up.
excellent. Thank you.